Hello and welcome to the course of Advanced Strength of Material. In this course, till now we have discussed about bending stress, and in the bending stress we have seen some problems also in the last lecture. Now in this lecture we will see the about shear stress in the beam. So after in a beam, whenever a force is acting, at that time two kind of action may happen. First, there is a bending moment and there is a shear force. So due to bending moment, the stress which is generated due to bending moment is called shear stress, and the stresses which are generated due to shear force is known as shear stress. So in the previous lecture we have completed the discussion about bending stress. Now in this lecture we will be discussing about shear stress only. So understand one thing, that whenever a beam is supported by some load, whenever a beam is supported by some means and a point load or any kind of load is acting in the beam, what will be the first consequences? Or first consequences is, due to this force this beam tends to deform. Now this beam tends to deform. Now this deformity is registered by the beam, and by this resistance it generates some stress inside the body. So that stress can be bending stress, or that can be shear stress. When it is shear stress, that is known from our shear force and bending moment diagram. So in a beam we can draw the shear force and bending moment diagram like this. So here in this case the bending moment shear force diagram will look like this. This is your shear force here, and the bending moment diagram look like this. So for this case, so bending moment diagram look like this. Here will be the maximum bending moment. So in this type of case, what happened, at the point of maximum bending moment shear force is 0. Only at that point bending stress will act. Other than this point, shear stress will be present in the body, and those value of the shear stress we have to know, and we have to understand about the value, how the value of the shear stress can be calculated and how they can be used. And for that this lecture is important. So in this lecture what we will know, our lecture objective is to understand the shear stress that induced in the beam due to what? Due to shear force. So let's start. So what is shear stress? To resist the shear force, the element will develop some resisting stresses or resisting forces. So that forces per unit area is known as shear stresses or tau. So shear stress is equal to shear force by cross sectional area, that is S by A. Now for example, in this figure, if we want to calculate the shear stress, then the shear force S will be, so this is your force that is acting in upward direction, but shear force will act on the transverse direction. That means the direction of the shear force will be parallel to the action of the force, parallel to the line of action of the force. That will be the direction of the shear stress. And the shear stress, for easy understanding of the shear stress, you can take a book, and you can if you take a book, and if you want to push it so that it can move from its place. So by pushing, you can see the book is not easily the book is not easily moving from its place, but instead what is happening, you can see that pages are, or the pages are becoming some getting some inclined shape first. So this inclined shape is known as, this type of deformation is known as shear. And this shear deformation, due to this shear deformation, is generated where? It is generated perpendicular plane. It is generated at the parallel plane of the line of action of the force. Now shear stress here, for example, see here, the shear stress will be, the force is acting perpendicular to this plane but parallel to this plane. The plane is this is our plane, that is BD. The area of this plane is BD. So in this plane, due to this force, the action or the stresses generated in this plane is known as shear force or shear stress. So how can be given by S by B into D. Now in the beam, shear stress are usually maximum at the neutral axis. So in a beam, shear stress are usually maximum at the neutral axis of the beam. Okay. Always if the thickness of is constant, or if the thickness at the neutral axis is minimum for the cross section, such as I beam, T beam, etc. And but it is zero, so shear force will be zero at the top and bottom of the cross section, as the normal stress of the cross section, as normal stress are maximum or minimum. So in that case, so what is happening in the case of shear force, at the neutral axis shear plane will be, shear stress will be maximum. Why? Because at the neutral axis the bending moment is zero. So as the bending moment is zero, there is only shear force is acting at the neutral axis. So in that case, the shear force, shear stress will be maximum. Maximum in the case of neutral axis, and at the top and bottom portion bending moment is maximum, so shear force must be zero, so shear stress is also zero. So that is how the shear stress distributed among the beam. Now see, so when a beam is subjected to a loading, both the bending moment M and the shear forces, that is V, act on the cross section. See what I am saying, that both the forces act in that cross section. And so if we consider a beam of rectangular cross section, so we can reasonably assume that shear stresses, that is tau, act parallel to the shear force. So tau will act parallel to the shear force, because that is where the shear force acts. Shear force acts as the at parallel plane with the line of action of the force. So we can say that shear stress on one side of the element are accompanied by the shear stress of equal magnitude acting on the perpendicular faces of an element. Thus there will be horizontal shear stresses between horizontal layer of the beam, as well as vertical shear stresses between vertical cross section. That means the shear stress always stay in a pair, and that pair will be perpendicular, and that means each and every plane will be in shear of a, so in this bar, see in this bar, these are the horizontal shear stress and these are the vertical shear stress. So this type of combination is seen in case of shear stress. So for horizontal shear stress, this horizontal shear stress occurs due to variation of the bending moment along the length of the beam. So from the bending moment diagram we can see that bending moment is 0 at a point, and it can be maximum, again it can be minimum. So this type of variation can be seen in case of bending moment. So now, so throughout the length of the beam, this bending moment variation can create horizontal shear stress. So if we assume two sections, that is PP and PQ, which are a small distance dx apart, which can carry the bending moment and the shear force M and S, and M plus MM, M plus del M and S plus del S respectively, as shown in this figure. So if we consider a small element, that is P dash, P double dash, Q double dash, and area of that element is dA, between the section PP and QQ, P dash and Q dash, this cylinder is at a distance y from the neutral axis. So this is at the distance y from the neutral axis. So we know the bending stress at P double dash will be, the bending stress at P double dash will be how much? From the bending equation we know the bending stress sigma is equal to m by I into y. Similarly, the bending stress at Q double dash will be sigma plus del sigma, that is m plus dm by I into xy into y. So forces due to this resistance shall be equal. So forces due to stresses at P and Q shall be Fp sigma into dA, and Q double dash sigma plus dA, plus del sigma plus into dA. Hence there is unbalanced horizontal force in the cylinder. So unbalanced horizontal force will be Fh is equal to Fq minus Fp, that will be is equal to dm by Iy into A. So this unbalanced horizontal force is resisted by the cylinder along its length, and in form of, and it is along its length in the form of shear force. This shear force, which act along the surface of the cylinder and parallel to the main axis of the beam, include horizontal shear stress in the beam. So that induces the horizontal shear stress. Similarly, this type of vertical shear stress are also induced by this bending moment only. So now we will see about some shear planes. So for rectangular section, what happened for rectangular section? For rectangular section, there is neutral axis. See, this is neutral axis. At the neutral axis, what happened? At the neutral axis, the section will have the maximum shear stress, and the shear stress distribution looks something like this. The shear stress distribution looks something like this. Now for the circular section, that is our neutral axis is in the center, and here also, as the symmetric section we can see, here also at the center or at the neutral axis, the tau max will be maximum. And in case of and in case of circular section, tau max will be maximum in the center, and the shear force or shear stress will be zero at top and bottom, because at the top and the bottom the bending moment is maximum. As the bending moment is maximum, shear force is zero. As the shear force is zero, there will be no shear stress. So that is it. These two section. For rectangular section, for triangular section, the Na will be at h by 3. But the tau max will be at h by 2 at the middle of that triangle, and at Na, in this case of triangle, at Na, tau max, tau average we can see at the Na. So at the neutral axis there is tau average in case of triangular section. Now in case of hollow circular section, what happened? In case of hollow circular section, what happened? That the image looks like this. The shear stress distribution looks like this. first, mm, in the in this part in this part the shear stress will be some will have some value. Next, the maximum value will be at the Na, and at that point, at the maximum shear stress point, there will be no material, so the material is cut out from here. So this is for hollow section. Now for hollow rectangular section, the shear stress diagram look like this, and for I section the shear stress diagram look like this. This shear stress diagram should be remembered because these diagrams come into your exam directly, and as a MCQ, as a short question also, and you have to draw this diagram. And another thing, there is no problem or no numericals in this topic for your in your syllabus. So, and the derivations are also not there. But remember one thing, there is two type of the shear stress. First one is horizontal shear stress, and that horizontal shear stress is given to you by the by this value, by unbalanced horizontal force in the cylinder, that is dm by I y into a into dA. Okay, this will be not a, this will be dA. This will be dA. So now another thing we will see, that is the vertical force. The vertical force that we. So now we will see about the vertical shear stress. That is, here we have already seen that how our here we have already seen that how the horizontal shear stress is happening. Now we will see about the vertical shear stress. So now if we see the derivation of the shear stress distribution across the beam section, what we can see, that if we consider a section PP and PQ as previously, and if we determine the magnitude of the horizontal shear stress at the level AB, and which the distance y from the yi from the neutral axis and the section above AA is assumed to made by the number of elemental cylinder that has area dA, and the total unbalanced horizontal force will be calculated. So total our horizontal force is dm by I into y into dA, that we have done in the last part. Now from y1 to y1, the whole thing from y1 to yt, at this position the fm will be or total force or total unbalanced force will be dm by I into y y bar a, that is our area of the centroid. So now horizontal shear stress shall be registered by shear area parallel to the neutral plane, and horizontal resisting area will be distance of the centroid of the area above AB from the neutral axis, and A area of the section above AB. So AH is equal to AB into AA bar B into is equal to B into dx. Now the horizontal shear stress will be shear resisting by horizontal shear force. So that would be our dm by dx into a by b, and we know shear force is defined as s into dm by dx. Therefore horizontal shear stress acting at any level of the cross section. So so therefore horizontal shear stress acting at any level of the cross section is given by our shear force. So that is it. So now So now from this we can say we have seen to how to determine the total. So this is our value of one elemental strip. Now for total elemental strip, for total section, we have to integrate this part. So for total section we have to integrate this part. We have to integrate this part from 0 to y max. So when we integrate from 0 to y max, we can see what we can see. We can see that our shear force will be is equal to dm by dx, and the value of the value will be the value of the of our total unbalanced force is nothing but it is equal to dm by dx. When it is equal to dm by dx, we can say that this unbalanced force is nothing but the sum of the total shear force that is acting on the body. So that is how the calculation or the how the shear stress can be calculated, and that calculation or derivation part is not very important for you. But main important part for you is to know about this picture, know about these diagrams. So these diagrams are very important, so you should remember these diagrams, and you have to remember what is shear stress, where the shear stress is acting, and how the shear distribution can be calculated, or how the shear distribution will be in the different sections. So that's it. If you have any problem, you may ask in the live class. Thank you.